All right, these are the collisions and bounce slides. So just to review momentum, objects in motion remain in motion. That property of all material bodies is what we call momentum. Momentum is inertia in motion. It is the product of mass times velocity. It is a vector quantity, which means it does have a direction. And the unit for momentum is kilogram meters per second. So in order to change momentum, something called an impulse must be applied. Impulse is change in momentum, and it is the product of the force applied multiplied by the time interval that that force is applied. Now, if we look at some things that are true about impulse, well, impulses always occur in pairs because we know, according to Newton's third law, that for every action there's an opposite and equal reaction. We know that those force pairs are simultaneous, which means they occur for the same time interval. So if the force pairs are the same and they occur for the same time interval, that must mean the impulse is the same because impulse is the product of force times the time interval. So impulses must always occur in pairs. They're always equal in magnitude. They're always oppositely directed. They always occur simultaneous. They never cancel because they act on two different bodies. And these look very similar to the force pairs that we learned about in Newton's third law. So this implies a couple things, right? So we learned about the law of conservation of momentum. In other words, momentum cannot be created or destroyed. It can only be transferred from one place to another. So momentum is like money in the room. So it can only be it can change hands, but the total amount must remain the same. So then we talked about collisions, right? What is the transfer of the momentum? So in physics, a collision is any interaction that produces a change in momentum of an object. So there are two types of collisions, elastic and inelastic. So we looked at the elastic collision. So there's no lasting deformation, no heat generated, no sound generated. Objects tend to bounce off each other. Now, there's no such thing as a perfectly elastic collision, and you learn about that when you get to the unit on energy. So here are some examples of perfectly elastic, or close enough, because there's no lasting deformation. The objects tend to bounce. So billiard balls striking each other, tennis ball striking a tennis racket, bouncy ball hitting the ground, bumper cars at an amusement park. Now, inelastic collisions, they're marked by permanent deformation, generation of heat, generation of sound, and almost all collisions have, actually all collisions have some sort of inelastic collision properties. So here's some examples: a piece of spaghetti being thrown at a wall, a glass dropped on a hardwood floor, it's going to break, permanent deformation, two football players tackling each other, they're going to grab each other, sort of try to bring each other to the ground, two cars colliding. Now, now, all collisions have some sort of elastic and inelastic property. There's no such thing as like a perfect elastic or perfect inelastic, but it does land somewhere on a scale, right? But you can say a collision is closer to one end or the other. So now let's answer this question though. Like, why aren't cars made to bounce off each other for safety? So if we look at some impulse, if we look at a car hitting a tree, well, we know that they're going to apply the same force to each other, the opposite and equal forces. We know that they both applied that force at the exact same time for the same amount of time. Now they're equal and opposite, but they don't cancel out because one force is acting on the car, the other is acting on the tree. So which object experiences a greater impulse? Well, we just determined that the forces applied on each object are the same and they're applied for the same time interval, so the impulses must be the same. Now, which object experiences a greater change in momentum? Well, we just said that the impulses applied to each of these objects are going to be the same, so that means the change in momentum is going to be the same because impulse is change in momentum. Now, why is the effect of the same impulse different on these objects if they're the same? Well, if you look at that equation over there, we know that the masses are different, right? So we know that the forces are the same for the same time interval, but that car is going to have a much smaller mass than that tree. And you can see that that must mean that there's a larger change in velocity. So you can see that that car is driving and it stops. That's a very large change in velocity. And that tree is barely going to move. I mean, because it's connected to the earth and that has much larger mass than that car. So let's put some numbers to this and find out, well, why aren't cars made of rubber so they bounce off for safety? So if we put some numbers, if we have a car that's 1,000 kilograms and is moving at a rigid wall at 20 meters per second, well, the stopping force is applied over half a second. So it takes half a second to stop. Well, let's find out what the force is applied if that car just comes to rest. So that car crumples and it comes to rest. So we're looking for that force and we can plug in all the variables that we know. Now the biggest mistake that I see people make is they take 20 minus 0, but the final velocity is at rest. That car slams into the tree, it's at rest. The initial velocity is 20 meters per second because it's moving in the positive direction. So I plug every value in and I get negative 40,000 newtons. Now, what does that negative mean? Well, force is a vector. So if you look off to that diagram, you can see that that car is moving in the positive direction. Well, it just stands to reason that you're going to have to apply a force in the opposite direction to slow it down. That's why the force is negative. So let's look at that. So 40,000 newtons of force had to be applied in the negative direction to stop this car going from 20 to 0 meters per second. Now let's look at the same car, except now this one is made out of rubber. So same mass, 1,000 kilograms, moving toward a rigid wall at 20 meters per second, except now it rebounds. So it bounces and rebounds going in the opposite direction at the same speed. So different direction. So negative 20 meters per second. And it takes the same amount of time. Stopping plus rebound applied over time interval of 0.5 seconds. What was the average force applied to the car during the elastic collision? Well, let's take a look at this. Now we're looking for the force. So I plug everything in, and I want you to notice what the change in velocity is. The final velocity is now negative 20 meters per second minus 20. So the change in velocity is going to be negative 40 meters per second, as opposed to the last one when that car came to rest, it was just negative 20. There's a larger change in velocity. So look what happens to that force. It's going to be basically doubled. That's why cars aren't made out of rubber to bounce off objects, because you just want one impulse to slow it down. You don't want to slow it down but then rebound it, because that's going to be a larger change in velocity, which means that there's going to be a larger impulse applied. So would you want to be hit in the head with a flat ball or a fully inflated ball? So the fully inflated ball is going to bounce and the flat ball won't. So we did this lab, we did the bounce lab. If we look at the bounce lab, there's a koosh ball and there's a bouncy ball. And what you do is you take them and you swing them into a block of wood. Now, what this is going to do, what this is going to do is they have the same mass. So we have the same mass, except one's going to bounce and one's not. And what you should notice is when you swing that koosh ball into that block of wood, it doesn't fall over. When you swing that bouncy ball into the block of wood, it does. Now, why is this, right? Well, in which scenario, if either did the ball hit the block with a larger velocity? Well, it's going to hit with the same velocity, because in both of those scenarios, it was the same string and you pulled them both parallel. So it's going to hit that block with the same velocity. Now, which ball had a larger change in velocity when colliding with the block of wood? Well, it's going to be that bouncy ball, because it hit the block going at the same velocity. However, it went in the negative direction. So there's a larger change in velocity as opposed to that koosh ball that just sort of stopped. So it went from whatever was going to 0. Now the bouncy ball went whatever it was going in the negative direction, a much larger change in velocity. So which means that impulse pairs. So yeah, if they're the same mass, but that bouncy ball has a larger change in velocity, it's going to apply a larger impulse to that block of wood. And so we have to use the concepts of momentum, impulse to explain how the koosh ball and bouncy ball had different effects on the wooden block when colliding with it. Well, because that bouncy ball had a larger change in velocity, it applied a larger impulse to that block of wood, which was a large enough impulse to knock it over. And the koosh ball didn't, because it just came to rest. One impulse to just slow it down. However, the bouncy ball basically had two impulses, one to slow it down, one to speed it back up. Applied those exact same, and the impulse pairs are the same, applied that same to the block of wood, knocked it over. So we know that the forces are opposite and equal. We know the impulses are opposite and equal. However, if we compare a flat versus full, well, the fully inflated ball is going to have a larger change in velocity. So what that means is that uh, the the fully inflated ball is going to hurt more, because, well, it's applying a larger impulse. It's the same mass, but the change in velocity is going to be a lot larger because it rebounds. Basically, two impulses. Your head has to apply one impulse to slow it down, one impulse to speed it back up. All right, so now let's talk about collisions and how they can be represented mathematically. So let's look at elastic collision. So what I want you to see here is that is the equation over there, right? M1 times V1 plus M2 times V2 equals M1 times V1 prime plus M2 times V2 prime. All right, so notice that the left side of the equation is before the collision, and the right side is after the collision, and they have to be set equal to each other because the conservation momentum, whatever you start with, you have to end with. Notice how the mass of the objects do not change, but the velocities do. So that's what that little prime represents, right? It doesn't change the math at all. What it does is it just says, okay, well, the objects are going to have a different velocity after the collision. So I have to denote that some way. That's what that little apostrophe means on the right side of the equation. So let's get some practice with this. Well, the red card has a mass of 3 kilograms and an initial velocity of 4 meters per second. The blue card has a mass of 1 kilogram and an initial velocity of rest. The cards collide in an elastic collision, so they bounce off each other. After the collision, the red cart has a velocity of 2 meters per second. What is the total combined momentum of both carts before the collision? What is the total combined momentum of both carts after the collision? What is the velocity of the blue cart after the collision? A lot to take in there, right? But let's just look at that red card, right? So we know all the variables. We can pull them out of that problem and we can plug them into our equation. So we know that that red cart, well, has a mass of 3 kilograms and is moving at 4 meters per second in that positive direction. So 3 times 4, well, is going to be 12 meters per second. Now the blue cart is at rest. Yeah, it has a mass of 2 kilograms, but it doesn't matter what the mass is. If it's at rest, it has 0 momentum. So the total combined momentum before the collision is going to be 12 plus 0. So it's going to have 12 kilogram meters per second before the collision. Now, after the collision, there has to be 12 kilogram meters per second of momentum after the collision because, well, you cannot create or destroy momentum, right? It's just going to transfer from one place to another. So then all you have to do is just solve that. So I know that after the collision, that red cart's going to have, it's moving at 2 meters per second. So it's going to have 6 kilogram meters per second. All I have to do is solve. So take 12 minus 6 divided by 1. And I know that that blue cart is going to have a velocity of 6 meters per second. So that those 12 kilogram meters per second, right, before the collision, after the collision, all this collision did was change where it was. It didn't change the total amount. So now let's look at inelastic collisions. So this is the equation now, right? So it looks like the exact same on the left side before the collision. I have two objects colliding, except now they're going to stick together. They're going to become one object, and you can see that on the right side. And once again, you cannot create or destroy momentum. That's why they're set equal to each other. So if we look at the right side of that equation, you'll notice that the masses are added together, and I only have one velocity because I only have one object. So let's take a look at an inelastic collision problem. So the red card has a mass of 3 kilograms, initial velocity of 4 meters per second. The blue card has a mass of 1 kilogram and initial velocity of rest. So this is the exact same scenario to that first one, except now they collide in an inelastic collision. So now they're going to stick together. So we have to find the total combined before, after, and what's the velocity of both carts once they stick together. So if we look at that first question, we already know that that first cart, we already know that the total amount of momentum before the collision is 12 kilogram meters per second. You plug everything in, you can do that. Except now I only have one object. Now they stick together. So the mass of that final object is now 4 kilograms. So all I have to do is take 12 divided by 4, and I get 3 meters per second. So these carts collide in an inelastic collision. They stick together, and now it's moving at 3 meters per second because I took 12 divided by the 4 kilograms, and I get 3 meters per second. So we applied all this to the rocket sled challenge, that final launch. So you can see here that the launches progressively got better, right? So the first one, you only had 3 people. The second one, there was a little bit more, there was more people, so you could distribute the mass a little evenly. And now we looked at that third and final launch. So now there was up to 8 students. So there's a little more room to play with, and you can have up to 4 students on a cart. Now, talked about recruiting. All right, so you could, okay, so now the key to this was mass distribution. You want to have more mass in the back parts of the carts than the lightest person on the front, because yes, the carts start at 0. The carts do start at 0 because they're at rest. Well, after the explosion, well, the total momentum still has to be 0, but you can distribute the mass, which would also change that velocity, and you want that front cart to go the fastest. Now, also, you want to make sure that you're applying the force with your legs. The legs are stronger than the arms, and they're longer. And you will probably want the tallest person or the strongest person pushing on these carts because they can provide a larger force for the longest period of time. Now, this was the scoreboard. This was the score after the launch. So you can see here the farthest was 6 meters, and that was that's It's pretty far. That's like maybe 18 to 20 feet, but that's pretty far, right? All right. So if we look at the conclusion questions, right, what's the total combined momentum of all the carts before the launch? Well, the total combined momentum is going to be 0. They're at rest. Now, the total combined momentum of all the carts after the launch, it's going to be 0. You cannot create or destroy momentum. Whatever the forward momentum is has to be balanced out by the negative momentum. So positive has to balance out with the negative, then total is still 0. We didn't create or destroy any momentum. So during the launch, which cart, middle or front, if either experiences a larger impulse? So if you can see off to that photo, that person's going to push on the front cart. Now, which means the front cart is pushing on the back cart. We know that those forces are going to be opposite. They're going to be equal. We know that they're simultaneous, so they occur for the same time interval. So if the forces on each cart are the same and they occur for the same time interval, that delta t, then we know that the impulses are the same, right? Because remember, impulse pairs are always opposite, equal, simultaneous. Now, this is the key to the whole thing. Well, during the launch, which cart, middle or front, experiences a larger change in velocity? It's going to be that front cart. It's because, well, yeah, you can't get over the fact that the impulse is going to be the same, and you start with 0 momentum and you end with 0 momentum, but the mass distribution can affect that. The lower the mass, the higher that change in velocity is going to be. The greater the mass, well, the lower that change in velocity will be. That's why that front cart launched farther than that back cart. All right, so once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.